Hello guys, today I would like to show few interesting theorems which are very important in calculus. They are mostly usable in proofs, but sometimes in calculations too. That's why let's just see them. Okay, and our first theorem is Fermat's theorem. Don't scare, it's not about the number theory. It is about something interesting. Suppose function is differentiable and at point x it has a local minimum or maximum, and then its derivative at this point equals 0. Seems like it's workable, but let's prove it. To do that, let's remember the definition of the derivative. It's those interesting limit f from x plus d minus f from x over d. So note that sign of d we don't know. Bigger than 0, less than 0, we don't know. It just goes to 0. So f from x is local point. Minimum or maximum we know just both cases, right? So then every point from x plus d or x minus d independent on the sign is strictly less or strictly bigger than f from x, right? And only the sign changes. This numerator sign doesn't change, only denominator. Then from the both sides of our point x, sign of derivative changes. Then for some positive a we have f from x minus a prime is less than 0, f from x plus a prime is bigger than 0, or another case. Then it's just visible, then f from x equals only 0, if it works for every small a. We can prove it, but I wouldn't like to do this because, seriously, let's just don't do this, right? Some more interesting theorem is Rolle's theorem. So what is the definition? If function f is differentiable on the interval a, b, and f from a and f from b are both equals 0, then f prime of c equals 0 such as c lies between a and b. It seems like something visible too, but let's prove it. So we have three cases. First of all, this gray point are a and b, and function in them both equals to 0. Then we have three cases. First of all, function firstly doesn't change. It just somewhere goes to 0, and derivative in every of this point equals to 0. And then we got this point c. The another case, function firstly grows up. Then to get 0 in the final, somewhere it has to go down. And it has somewhere the local maximum extreme point. The another case, just inverse, function goes down and has to go upstairs to get this point, and we also have the local extremum, the minimum point. And by the proved Fermat theorem, we know that derivative there is equal to 0. Then it is proved. The another useful theorem is Lagrange theorem. It requires f is differentiable again, but now we have something another. F from b minus f from a over b minus a equals f prime of c, such as c lies between a and b. Why is it truth? Why is it maybe truth? What is our hypothesis? Let's draw it. Now we can try to understand. Then this is our tangent line, right? This is our tangent, and it really can be tangent, which is derivative. But let's try to prove it more carefully. First, I'm going to integrate it. Let's call this x and integrate by the dx. Then we'll get some constant, but let's change it some. Let's add another constant to make our x movable, right? Now opening this all, we will get just another constant which is able in the integration. Move f with another sign on the another hand side, and say is all is w function from x. Then we have the Rolle's theorem about if w from a equals w from b equals 0, then w prime from x, which is we would like to get, equals 0 at some point, which can be c. Let's try to make it. We need to get those constant a and b such as that satisfies these both equations. Okay, let's suppose it is f from a, because seriously it will cancel each other there, right? And what is b then? This thing is something ununderstandable. That's why let's make b equals a to cancel this part. And look what can we do there. Well, the first equation worked, but what with the second? Seriously, it works. Look there. b minus a cancels. Then we have this thing and this thing there. It is the same, but with the negative sign. It means we got this function. Now let's go ahead. No, but let's go ahead more carefully. Starting with differentiation, replacing letter c back instead of x, and moving this thing on the other hand side. Yes, we did it. So let's change this theorem sum and get f from a minus f from b over g of a minus g of b. And it equals to f prime of c or g prime of c. It is something really understandable. We cannot just say it is truth because wait, we can try to use the Lagrange theorem proof and try to get something workable. Just remember what we had there. G was just unit, right? G of x equals x. But now it is something another. Just let's do the same thing, but the same proof. Maybe workable, the same proof. Yes, let's integrate it again, but firstly let's of course move g there. And what can we get again? We have this both equation, and of course let's again substitute a equals f from a and b equals g from a. Of course it works there, but there, what will be? Okay, x equals b. Then this side cancels with the negative sign, and this cancels with the positive sign. And again we'll get 0. It means it is workable. I wouldn't like to differentiate it back, just go ahead yourself if you want. Of course you proved it. It is a very unusual theorem, even more unusual than Lagrange's is. So let's remember the L'Hopital's rule. It's about unusual limits, where you have some fraction of the functions which are too complicated to calculate it. And then you can say that if both of the function going to 0 or to infinity with no matter how digit exactly, means we can rewrite it as the same limit with fraction of their derivatives. Let's take a look at 0 case because it's easier to prove. So function f and g has derivatives. It means they're continuous. So it means that if f from x, where x goes to a, it goes to 0, then f from a is 0. Just like this. This fraction is the same as this fraction. They are really the same because f from a and g from a are both 0. But by the Cauchy theorem, we can say it is f over g prime of c, where c lies between x and a. So it means if x is closer to a, then c is the same closer or even more closer to a too. That's why we can rewrite it as limit c goes to a of f from c over g from c. We just rewrote the another letter there. Instead of c, we wrote x. And this is proof. What about the infinity case? It is more complicated. Believe me, it is really difficult. So the L'Hopital's rule for infinity of infinity case is much difficult to understand and prove. But okay, what is our first thing to do? We'll get source point z, which is so close to a as g goes injective to infinity, because then we'll use the Cauchy theorem and denominator has to be not 0. I mean, it can go to 0 but not be equal to 0, right? Okay, that's why we get those z. And then we divide and multiply by the same constant, by the same function, which makes it like a Cauchy theorem. Then we divide by g to get the same limit and cancel key, which is the limit of the derivatives. Now we notice key times 1 plus 0 minus key. Let's move 0 to make more visible and take the absolute value in equation, which is called triangles in equation. Then we have 0, 1, 0 because x is enough big, makes it enough greater than constant. Same works there, if k is real, of course. And now, if k is real, we have proved it, because 0 times 1 plus 0 plus 0, and something we don't know, which is only 0. But what if k isn't real? For example, we have 1 over 0 and something like this. Suppose we have this case, then we just divide, yes, 1 over this thing, take each derivative or derivative. L'Hopital's rule now allows us to do this, our proof of it, of course. And now move everything back. And we are done. Injectivity of G requires in our proof to make this denominator never equal 0. Close to 0 maybe, but not 0. Yes? Of course. If we cannot say this point z, then we cannot use the L'Hopital's rule. Yes, and we have always to check that this point exists, and we can say that z point is on the way, but we don't want to do it, because seriously, if we don't have this point, like in this example, which is obviously 1 over 2, if x goes to infinity, then what can we say? Derivative of the denominator can be 0 in infinity set of points in the way to infinity. Then L'Hopital's rule wouldn't work. Let's check it. Yes, it won't. Because division by infinity, division by 0, and division by 1, 0 division by 1, and so on, goes to give us some set of values, not the only value in the way. If we have some point, then this baddest stops, then we say this is point z, but we don't have it, and we don't have the answer by using the L'Hopital's rule, but obviously it is 1 over 2. That's why just don't fear. Just if you see something like this, don't use this rule. It is wrong.